In the last video, we talked about energy, specifically kinetic and potential energy, and how those were related with this idea of the conservation of mechanical energy, basically converting one form of energy to another. Well, in this video, we're going to extend that a little bit and talk about two other properties that are really important in our discussion of energy, and that is work and power. Now, where this matters is to answer this question here. Where did the energy come from? So say you're standing on the ground, you're 80 kilograms, and then you climb up to the top of a diving board. Still 80 kilograms, but now you have some height. Initial and final, I don't have any kinetic energy there. The thing that's changing is my potential energy. So if I look at that, initially I had 0 joules of energy. We're going to say no potential energy because I'm on the ground, no height. But my final energy, mgh, I can calculate a potential energy here of 1,962 joules. So clearly my initial energy does not equal my final energy. Some stuff happened in between to somehow add energy to this system. Now I can see the same scenario in adding another form of energy. Say I push a cart, a really heavy cart of crate boxes, from 0 meters per second to 5 meters per second. So I am somehow adding kinetic energy to the system, and I can quantify that. My initial energy was 0. My final energy is just 1/2 mv squared. So 1/2 times 200 times 5 squared is 2,500 joules. Again, my initial energy does not equal my final energy. Some energy was added to the system, in this case, in the form of kinetic energy. So where does this energy come from? Well, in physics, we give this a name. We call this idea of adding or removing energy from a system work. Now, a tricky part about physics that we run into every once in a while is we use words that are pretty common in our everyday language, but they have very specific meanings in terms of physics. In this case, work is defined as a force being applied to an object where the object moves in the same direction as that applied force. So, two things that are important here. You have a force and you have a direction that force is going. Now we can calculate this and quantify this using those two ideas, the force and the displacement. Well, work is going to be represented with the symbol capital W, and that is equal to the force, capital F, times the displacement. You may remember from our SUVAT days, displacement is represented in IB as a lowercase s. Well, displacement is measured in units of meters. Force, as always, is measured in units of newtons. And the work has its own unit that actually matches our unit for energy. The work is measured in joules. This is really important because of that definition we were talking about earlier, where work is a way of adding or removing energy from a system. If it's going to add or remove energy, it better be doing so in the same units as what we're calculating our energy in. Now you'll notice here I've got a little asterisk on this equation because this equation, it only works in very specific scenarios. It only works if the force is constant, so the force that you're pushing with is the same the entire time, and that force is entirely in the direction of the movement. Now, that's good in really simple cases, like you're pushing a block across a table and you're pushing exactly the direction that the block is going. But in a lot of cases, we're not going to be in the same direction and we're not going to be constant the whole time. So let's talk about those features that kind of add to these other possibilities. So a reminder here is direction is going to be really important when we get into this because there has to be a force and there has to be a displacement. That direction kind of changes. That's that asterisk in that equation. So let's look at what that direction might do for us. Say I want to move this object, this block, across a table, and instead of applying a force that's perfectly parallel to the table, I pull up at some angle, but it moves across the table as if I were just pulling it horizontally. Now, we know from that definition that the force has to be in the same direction as the motion. In this case, that force isn't perfectly in the direction of the motion because the motion, it went from here to give me an overall displacement that was perfectly horizontal. But this force isn't perfectly horizontal. Even though it isn't, some part of it is. It isn't all horizontal, but there is definitely a component here that is horizontal. And we can calculate that by making it a right triangle. So figure out how much of that force is in that perfectly x direction, measured along with my motion. To do that, I've got an angle here with my adjacent side, my hypotenuse. I can calculate that using the cosine. Cosine of the angle is just fx divided by f. Solving that for fx, just multiplying both sides by f here, I get that fx is equal to the force times the cosine of the angle that the force is with my direction of motion. I'll remind you that the work formula that we talked about was force times displacement. So now, instead of just saying any force, I'm going to say this is the force that's in the direction of the motion. That was the fx that I calculated. And in terms of the force overall, I can plug in force times the cosine of theta, what I solved for fx here. Now, this equation is a much more generalizable equation that can handle the force not being perfectly in the direction, because direction is a component of that. Now, this isn't exactly the form that you see in the data booklet. Instead, it's rearranged slightly to say the work is equal to force times displacement times the cosine of that angle. That's what you'll see show up in that subtopic 2.3 in the data booklet. So let's dig into this formula and just make sure that it works for us in a variety of situations. And a good thing to do anytime you have a mathematical formula in physics is to test it against the extremes. So in this case, the extremes that I see are, what if you're pulling it perfectly parallel? So that initial simple case that we talked about. And what if you're not pulling it at all in the direction that it's moving? Like you're perfectly perpendicular, which is not at all in that direction. So let's look at this first one. If you're perfectly parallel, you're pulling in the direction of the motion, we say that the angle theta is 0. Now, what's important here is how does it interact with cosine? The cosine of 0 degrees, you might remember from your unit circle days, is exactly 1, which means that I wouldn't need to write this. Cosine of the angle I know is going to be 1, and anything times 1 is itself. So that just simplifies down to the work is equal to force times displacement. That was that simple asterisk form of the equation that we saw earlier that calculates work if the force is already in the direction of motion. This, honestly, is what we're going to be using most of the time. You won't need to deal with this cosine theta unless it's very clear that there's an angle, and it will be presented to you typically if that's the case. If our force is not at all in the direction of motion, it's perfectly perpendicular, we would say that theta is 90 degrees. The cosine of 90 is actually 0. So that means that this term in this equation is going to be 0. So anything for force or displacement is going to result in a work of 0 joules. That there is no work being done if the force is perpendicular to the direction of the motion. We'll see an example of that in a little bit. But first, let's actually use this. Let's plug in these values and see what happens to calculate our work. When you push a lawnmower, you're actually not pushing perfectly parallel to the ground in the direction that you're moving. Instead, you actually push downward, down the handle here at some angle to the direction of motion. I'd like you to calculate how much work do you do when you push a lawnmower 20 meters with a force of 200 newtons directed at an angle of 30 degrees with the ground. Again, this is your formula. What is the work being done to calculate or calculate the work being done here with this force, displacement, and angle? So really it's just a plug and chug. You just plug in your 200 newtons, your 20 meters, and your 30 degrees. That 30 degrees being the angle which you're pushing relative to the direction of motion. So you get 3,464 joules of energy that is ultimately added. So that joules, in this case, is responding to the work being done. So what I was alluding to there kind of gets at our last question, or that the question that we started this whole thing with, is work is a way of adding energy to a system. So you're pushing on the ground, you can add energy to the overall system of that lawnmower. We call this the work energy theorem. If energy is truly conserved, like things would never be able to start or stop moving because you never have energy different before or after. So energy is still conserved. We don't say that it's created or destroyed It's just being transferred from one system to another. So, for example, if you're pushing on a block, you're just converting some of your chemical energy in your muscles into a kinetic energy of something else. So you're just transferring it from one thing to another. You're not actually creating energy, but you're transferring it in the form of work. So let's see an example of what that actually looks like here. Say you have an engine that applies 1,000 newtons of force over a distance of 50 meters. You started from rest and your car has a mass of 2,000 kilograms. How fast are you moving after traveling that distance? This is a classic work energy theorem sort of problem. What I think is useful to frame this is to again think of it as initial energy and final energy. My initial energy, I'm not moving at all. So I say that my initial energy is 0 joules. If I want to find how fast I'm moving after traveling a certain distance, ultimately my final energy that's going to be useful is how much kinetic energy did I gain? 1/2 mv squared. But before I get there, let's figure out where the energy is going to be coming from. That energy is going to be added using work. Work, we said, was calculated force times displacement. In this case, the engine is applying a force of 1,000 newtons over a distance or displacement of 50 meters. So 1,000 times 50 will find my work in joules. That is 50,000 joules. So if I started with 0 joules of energy and this engine produces 50,000 joules of work, that means I have added 50,000 joules to my system, so my final energy is now 50,000. That is really useful and interesting to know, but that's not actually what I'm asked here. I was asked, how fast are you moving after traveling that distance? This final energy I know is kinetic energy. I didn't gain height in the process, so all of this energy is kinetic, and I can find that velocity by just setting it equal to that final energy. 1/2 mv squared, the mass being 2,000, is equal to my final energy, 50,000 joules. Solving for v, I can find that my velocity is about a little over 7 meters per second. So again, my initial energy is 0, my final energy is 50,000, and I knew that final energy by calculating the work. Work is a force being applied over a certain distance, and that is adding energy to the system. This also works on the opposite side as well. If I have a 75 kilogram skateboarder kicking off with an initial velocity of 2 meters per second, and then eventually coming to a stop because of the force of friction, I can figure out the force that's acting here. In this case, my initial energy is converted to a final energy of 0 joules. I can also calculate the initial energy, though. That's all kinetic energy, 1/2 mv squared. The mass is 75. The velocity is 2. So I can calculate an initial energy in this case of 150 joules. Now, my initial energy had to go somewhere. It was dissipated by friction. It ultimately gets transferred into like energy of heat or thermal energy or sound energy. But the way it gets dissipated is by transferring to the work being done by friction. Work can be a way of adding energy. It can also be a way of removing energy from the system. Work, in this case, has to be 150 joules because that's my delta between the initial and the final energy. That's how much it changed by. And that must be equal to my work equation. There is no angle here, so I'm just going to use force times displacement. And the displacement, I know it came to a stop after 15 meters. So the force of friction was applied for 15 meters of distance. So F times 15 is going to be equal to that 150, which means that the force has to be about 10 newtons. Now you could actually calculate this using our understanding of forces and our understanding of suvat, that you could find the acceleration and use F equals ma to find the force that way as well. But this is another method that can be really, really handy in doing that, just comparing the energy before and after, and the difference being the work. So that gets us to a couple like weird scenarios that show up sometimes with work. If you have a waiter carrying a heavy food tray at a constant velocity across a room, are they doing any work on the tray? Well, if you think about it, the force that they're applying is straight up, and the motion, that displacement at a constant velocity, is sideways. So technically we say no. The force is not in the same direction as the displacement, so they are doing no work on the tray. Another way to think about it, though, is it didn't change the tray's energy at all. If they're moving at a constant velocity, you're not adding any kinetic energy. And if they're holding at the same relative height, you're not changing its potential energy either. So there's no work being done because you're not changing the energy. If you push on a wall, and you can push really, really hard, but the wall doesn't move, you're not doing any work there either, because there's no displacement. And turns out you're not adding any energy to the wall. You're not making it move. You're not giving it height. So work can only be done if you're adding or removing energy from a system. Another example is Earth's gravity on the moon. Is Earth's gravity doing any work on the moon? Well, the answer is no. It's not doing any work on the moon because the force is inward towards the Earth, and the displacement is always always moving perpendicular to the direction of the force. So just like we saw, if the angle is 90 degrees from the motion, you have zero work. An example that's shown up in a past IB exam just states particle of mass m is moving at a constant speed v, uniform circular motion. What is the total work done by the centripetal force during one revolution? The answer is zero. So it's an example of something that looks like you need to calculate something, but no, it's just checking to see if you understand the idea that if the force and displacement or force and motion are perpendicular, there is no work being done. All right, one last example of work. Let's say you have two physics students, Maria and Paige, that are going from the first floor to the second floor. Maria walks and does that 3-meter staircase in 15 seconds, and Paige runs that 3-meter staircase in 5 seconds. Let's say they both have a mass of 60 kilograms, which means to move at a constant velocity, they are applying a force equal and opposite to the force of gravity. Who does the most work? Well, it's kind of counterintuitive here. Turns out that they do the exact same amount of work, because work only depends on force and distance. So if they're moving at a constant velocity, both are going to experience the same force. They're counteracting gravity, and they have the same mass. And they're going the same distance, so force times distance is going to be the same work for each one. But the reality is, that situation, and one certainly feels different than the other. So it feels weird to say that the work is the same for both of them. So something is changing. It's just not work. Instead, it's something called power. Power is the rate at which work is done. This is why you feel more tired when you run up the stairs, because you're exerting more power, more work per unit time. And just real quick, we can calculate power just taking the work divided by time. So capital P for power is capital W over lowercase t. Time is in seconds. Work is in joules. And then power, we're going to represent using units of watts. So I wanted to present this here because we will see power quite a bit later on this year. Right now, we're going to kind of gloss over it. We'll come back to it later on. This power in watts is the same watts that you might recognize from an understanding or familiarity with electricity watts, that different appliances use different amounts of power, and that can be converted from a mechanical power to an electrical power if you wanted to, just by looking at how much work is being done per given unit of time. So the main takeaways here is you should be able to define and calculate work using that equation Fs cosine theta. You should be able to calculate work when the force is that angle, and then equate work done on a system to change the energy of that system. And ultimately, with that, using the work energy theorem to solve for some unknown. So in the examples that we saw today, we solved for force. We also solved for final velocity, just using the understanding that work is adding energy or removing energy from a system. And then finally, you should be able to identify situations where there is motion, but no work is being done. or where there is force, like pushing on a wall, but no motion, so no work is being done there either. Work is a way of adding energy or removing energy from a system.